What's the first thing that comes to your mind when you hear the word halogen? Most people probably immediately start thinking about halogen light bulb. They are common in automobiles, headlights, stage lights, and commercial light fixtures. These light bulbs get their name because they are actually containing bromine or iodine, which belongs to the halogen family of elements. Although the halogen plays an important role in the lighting industry, do you know that they are also commonly found bonded to organic molecules? That's right. In fact, organic compounds that contains halogens find wide use in pharmaceuticals, materials, and polymers, all which we depend on our daily lives. In this lesson, we are going to be exploring about different methods of preparation of haloalkanes and its physical properties. Basically, there are three methods of preparation of haloalkanes: from alcohol, from hydrocarbons, from halogen exchange. The first method of preparation is from alcohol, where the hydroxyl group of alcohol is replaced by a halogen on reacting with halogen, acid, phosphorus halide or thionyl chloride. Here, thionyl chloride is preferred because along with the formation of alkyl halide, two gases, sulfur dioxide and hydrogen chloride are also formed, which are escapable. Hence, this reaction produces pure alkyl halides. Whereas, primary and secondary alcohol with HCl requires the presence of zinc chloride, which is a catalyst. With tertiary alcohol, the reaction is conducted by shaking the alcohol with concentrated HCl at room temperature. To obtain a good yield of alkyl halide, alcohol needs to be heated with sodium or potassium iodide in 95% orthophosphoric acid. In this reaction, phosphorus tribromide and triiodide are generated in the reaction mixture by the reaction of red phosphorus with bromine and iodine. Whereas in the method of preparation from hydrocarbons, free radical chlorination or bromination of alkane releases a complex of isomeric mono and polyhaloalkanes, which is difficult to separate as pure compounds. Hence, the yield of any single compound is low. For example, the chlorination of butane produces 2-chlorobutane and 1-chlorobutane. The second method for the preparation of haloalkane is from alkenes. Under that, we also have two methods. The first being the addition of hydrogen halides, where an alkene is converted to corresponding alkyl halide. Here, the HX is the hydrogen halide and the value of X can be chlorine, bromine and iodine. The second method is the addition of halogens. Here, the addition of reddish-brown bromine to ethylene in carbon tetrachloride produces a colorless vicinal dibromide called ethylene dibromide. Next, the third method is by halogen exchange. Here, the alkyl iodide can be prepared by the reaction of alkyl chloride or bromides with sodium iodide in dry acetone. This reaction is called Flinckstein reaction. Yet another reaction is the Schwarz reaction, where alkyl fluoride can be obtained by heating an alkyl chloride or bromide in the presence of metallic fluoride such as silver fluoride, mercurous fluoride. Let's now move on to the method of preparation of haloarenes. We can obtain aryl chlorides and bromides by electrophilic substitution of arenes, such as toluene with chlorine and bromine separately, in the presence of Leavitt acid catalyst like ferric chloride. The ortho and the para isomer obtained in this reaction can easily be separated as their melting points are different. Fluorocompounds are not prepared by this method due to high reactivity of fluorine. To prepare a haloarene from an aromatic amine, first we need to dissolve the primary aromatic amine such as aniline in cold aqueous mineral acid and treat it with sodium nitrite. This reaction will produce a diazonium salt. This reaction is known as Sandmeyer's reaction. The second step will be to mix the solution of the freshly prepared diazonium salt with cuprous chloride or cuprous bromide. In this reaction, the diazonium group will be replaced by chlorine or bromide. We can see that for the replacement of diazonium salt with the iodine, we need to mix it with a cuprous halide. We simply need to shake the diazonium salt with potassium iodide to obtain the aryl halides. Let's now discuss the physical properties of haloalkanes and haloarenes. First, we will start with the color. The pure alkyl halide are colorless in nature. However, bromides and iodides exhibits color when exposed to light. Next, if we talk about the smell, there are many volatile halogen compounds that have a sweet smell. On the other hand, the intermolecular force of attraction of the halogen derivative are very strong due to their polar nature, as well as the higher molecular mass of compared to the parent hydrocarbon. Hence, the boiling point of chlorides, bromides and iodides are higher as compared to the hydrocarbons of the same molecular masses. You can see here the pattern of variation of the boiling point of different halides. For the same alkyl group, the boiling point of alkyl halides decreases in the given order. Similarly, the boiling point of isomeric haloalkanes decreases with increase in the branching unit. For example, 2-bromo-2-methyl propane has the lowest boiling among the three isomers shown here, whereas the boiling point of isomeric dihalobenzenes are almost the same. However, the melting point of para-isomers are higher than that of ortho or meta-isomers. Due to the symmetry of the para-isomers, these isomers have a better fit in the crystal lattice as compared to the ortho and meta-isomers. The next physical property is density. The bromo, iodo and polychloro derivatives of hydrocarbons are heavier than water. Here, the density of the derivatives increases with increase in the number of carbon atoms, halogen atoms and the atomic mass of the halogen atoms. The final property we will discuss is the solubility. The haloalkanes do not dissolve easily in water. They are very less soluble in water. The reason behind this is, for dissolving haloalkanes in water, energy is needed to break the strong intermolecular force of attraction between the haloalkane molecules and for breaking the hydrogen bond between the water molecules. Even after breaking the bond, the new bond that is set up between the haloalkanes and the water molecule is not as strong as the original. However, the haloalkanes dissolves easily in organic solvents, as the new intermolecular bonds between haloalkanes and the organic solvent molecule are equally strong as the ones that has been broken. As we are now clear with the physical properties of haloalkanes and haloarenes, now try to answer one question based on the properties. In which of the following solution the haloalkanes will dissolve easily? Petrol, water, alcohol. Try to figure out. Let's now summarize what we have learned.
Manorama Horizon. Learning made simple.